This week we're going to talk about project control on a construction site and then have a real brief review of both horizontal and vertical control calculations. So when we talk about control, it means a lot of different things in surveying. Control can mean a reference point really for any application on a job site. And I've got some examples here of an RTK GPS control base. It can mean a big target panel point for aerial photography back when it used to be done primarily by airplanes, as recent as 5-10 years ago. Anymore, people are performing kind of their own photogrammetry with the advent of drones. And you can see here's my little drone in the photograph, and sometimes all you need to do is put a cross of lath painted up pink, and these show up actually from a 400-foot altitude. This other picture here is something I did actually just yesterday, establishing some control points around a project site for that final project I'm working on for the environmental degree. A control point can be um, predetermined and established for use in the public, and we're going to look at this in the GPS surveying class, but this just happens to be kind of a commemorative control point over at Pompey's Pillar. They publish the latitude, longitude, and elevation for people. I don't know that it's really used in a commercial sense, but it's kind of neat for people to look at. And one of the ones that I always think is really neat to see pictures of are these Walt Disney World specialty monuments. I believe they have Bernstein Manufacturing Company produce these for them. Control can also mean boundaries. Here's actually a horizontal traverse control point, and you can see here in the image that's where the boundary control point ended up being. And I put a drill hole in the top of that little concrete retaining wall and actually set a mag nail, so hopefully it'll be there for years to come. This is an abstract or a portion out of the Montana Department of Transportation's Survey Control Manual, and they talk about when a control survey is required, and you can see they're basically talking photogrammetry, new construction, reconstruction, bridge replacement, safety, and any project that uses a data collector. So essentially, all survey projects require some sort of control on a job site. And this class is going to look at control for a construction site. We're going to establish control to be used as reference points to lay out a series of points in various route surveying applications. We have two types of control on a job site, both horizontal and vertical. A horizontal control point is essentially a traverse point, and a vertical control point is what we've learned now to call a benchmark. Horizontal control can be established primarily right now with two different tools. You can perform a horizontal traverse and use a total station, just like we did last spring in the Intro to Surveying course, or you can use GPS in either a static or RTK, which is a real-time kinematic application. And we'll be looking at both of those applications in the GPS surveying course later this semester. Just as a quick sidebar, this was a rental robotic GPS I used, and this is a quote-unquote smart tracking prism. That's a $2,800 prism, so I was real careful to not drop that thing that day. Vertical control, we've also looked at two of these three methods. Probably the most common, the most accurate, is differential leveling with an automatic level. We also looked at trigonometric leveling by using the zenith angle and the slope distance from a total station. And we'll look at this in the coming weeks in the GPS class. You can also establish a good vertical component or a z coordinate with GPS using either static or RTK methods. These again come out of the Montana Department of Transportation's survey manual. They talk about some of the requirements for their surveyors when they're establishing horizontal control and vertical control on a job site. If you're a subconsultant working for MDT on an MDT job, regardless of your personal comfort levels and allowances with certain tools, you have to conform to their standards and their requirements. So it's good to know where their requirements are located and what they are. Control requirements. They have to be convenient for use, so meaning they have to be close to the job site so that they're practical to use. You don't want to be shooting a total station, honestly, more than probably 300 or 400 feet, especially if you're going to use trigonometric leveling to get elevations on those points. You know, a total station can easily shoot over a mile now to a prism, but you have to balance the ease of that data versus the accuracy of that data. And just because it can shoot that doesn't mean you should be using the data. It also has to be accessible. Generally, we like to be able to drive to a control point because we're going to be carrying some bulky and heavy equipment. So vehicle accessibility is primarily what people seek when they're choosing good control point locations. Has to be protected. Generally, we mean protected from equipment, from damage, from disturbance. And a real common thing to do is to build a bird cage around a control point. And there's a kind of a sketch on page 19-14 of the textbook. It needs to be clearly marked and understood by both you and the contractor so that they know what points they're looking at on site. Needs to adhere to naming and numbering conventions so that there's no miscommunication within the office or on the job site. And it needs to be documented in your field notes, typically through a control legend or a control abstract and a vicinity sketch. So let's look at each of these individually here. Convenient for use. I'll go back to this other picture of GPS. You can see this is kind of at the top of the mountain. I had about a mile of a project vicinity this day, and I wanted to get my GPS broadcast up as high as possible. And I did not want to carry a 10-pound battery and legs and a GPS receiver up to the top of that mountain, so I made sure I'd set it where I could get my truck to it. And then in town, in an urban setting, convenient means not needing to shoot long traverse legs. So you can see the back sight is down here in the distance. I've got a traverse point just out of frame in the photograph, and I'm only shooting a foresight point about 8 feet away, 10 feet away maybe, to a property corner here. Real convenient for one person to do, real short sights which minimize any angular error that could be introduced by me or the tools in this job, and provided a really good closure on this traverse. Here's some bird cages we're building on a project we did up in the Boulder Cemetery. This is a little bigger than I like to, that takes up quite a bit of space, but essentially you put 3 lath around your control point, you wrap some flag around it so it's easy to see, and a person's really going to have to go out of their way to damage the monument, whatever you've set in the ground in the middle of that cage. Plus, these lath actually serve as your tablet out in the field. You can write the name of the control point, possibly the elevation if you want to report that, and they just they convey information to both you in the future and other users who weren't there the day that that control was established. Sometimes protected doesn't mean putting a lot of things to warn everybody about a control point, but it means being discreet and almost incognito. And when I'm setting my own control points on a job site, Oftentimes I don't want people to know that they're in the ground. So actually this one's kind of hidden by the tripod leg here, but my traverse point, I simply put a little pin flag. You can kind of see the pink there of my pin flag, just so I could find it the rest of that day, and then I took that pin flag out. I'm the only one that knows where this thing is, and it's set low enough that a lawnmower won't disturb it, and sometimes that's what you do to protect things. We're going to look at these last three requirements together because they all kind of complement one another. Clearly marked and understood, adhering to naming and numbering conventions, and documenting them in the field. And these are examples, again, from NDT's survey manual. Their convention for naming control points is to go along the center line of a road, because obviously they're always working along roadways. On the left-hand side, in the direction of travel, they number their control points based on the mile marker. So this is a little unrealistic because I don't believe there's any roads in Montana that have mile markers that go into the thousands, but this would indicate that you're between mile marker 1234 back here and 1235 over here. And as you proceeded in the direction of travel, once you hit mile marker 1235, then the numbering starts over, and your numbering begins with 1235. So you always know where you are along an MDT roadway based on the control point, which is reflective of the mile markers. The letter refers to the sequence. They go alphabetical, starting with A along the left-hand side of the roadway, A, B, C, D, E, and if you have to jump over to the other side of the road, for visibility, for protection's sake, for accessibility, they work backwards, J, K, L. So you always know kind of where you are, left or right of center line, near the mile marker, or further down travel from the mile marker, based on the simple naming and numbering convention of an MDT control point. And then they also require a control point abstract, and this is their example set of field notes. And an abstract is just a description of what was that control point's name and number, what's the actual monument in the ground, and are there some reference ties to physical features out there that are going to help somebody find it. If there are, you put them in a little sketch. Levels of control. Our textbook gets into this a little bit on page 19-14. Primary control means permanent control. It's the most important control you've established on your job site. You don't ever want anything to happen to it. You've put the most time and care, used the best survey methods and procedures to establish it, and it is your prime series of reference points on a job site. Generally, you're only establishing primary control through closed horizontal traverses, so a closed loop, or you're using static methods for GPS, which are slower and not as immediate as the results from real-time kinematic, but generally they're better. Once you start building off of primary control, we call that secondary control. So if you're performing a resection, which we can talk about that later on this semester, but a resection is essentially turning one angle and two distances off of two existing primary control points and using some trigonometry to set a new point. It's not part of a closed loop, which means it's not as confident in its position as primary. Or if you're just setting kind of a dogleg stub off of a primary traverse, you're leaving a control point dangling out there with an angle and a distance, and you're not closing it to anything. That would be considered secondary control. And if you start building off of secondary points, then you're into your tertiary level, and that really becomes unusable for construction applications because you just don't have the confidence in its position to guarantee what you're staking is going to be where it needs to be. And that leads to a concept addressed in the textbook that's really important on a job site. Be twice as good as the person coming after you. And what we mean by that is if a contractor's building tolerance on a job site is 1/4 inch, you need to be 1/8 of an inch good with your control. If they're a 1 inch tolerance accuracy, you can be 1/2 inch accurate with your control. You don't want to eat up all of the contractor's tolerance in your control. So that's a good rule of thumb, is always ask the contractor, how good do you need to be with your caissons, or your pilings, or your well locations, or your manhole locations. And that lets you know what tools to use and what level of control you might be able to live with when you're staking things out for that contractor. Quick review of horizontal and vertical control calculations. We've done this in the Introduction to Surveying course. So we'll look at horizontal really quick. Recall if we have 2 control points, control point number 1 and control point number 2, they're related to each other by both an azimuth and a distance. And any line that we've established in surveying can be reduced into easier components to work with. A vertical component that we call a latitude, and a horizontal component that we call a departure. And you'll recall in our calculations that a latitude is equal to the distance times the cosine of the direction, or the cosine of the azimuth of that traverse line. And similarly, a departure is equal to the distance times the sine of that exact same direction, of the azimuth. If we add a direction and a distance to this example, an azimuth of 110 degrees, 30 minutes, 15 seconds, and a horizontal distance of 1,050 feet, we can compute the latitude and departure, or the northing component and the easting component of line 1, 2. Latitude is going to be 1050 times the cosine of the azimuth, which is a negative 0.3502755, or a latitude of a negative 367.79 feet. And remember, these signs are important. Negative indicates we are going less latitude, or south, in our direction to get from 1 to 2. And that's the beauty of using an azimuth as opposed to a bearing, is that if you use the azimuth, the trigonometric function will give you the correct sign indicating the direction you're proceeding with respect to your north. The departure would be 1,050 feet times the sine of the azimuth, and the sine of 110, 30, 15 is a positive 0.9366467, or a departure of 983.48 feet. And because it's positive, we know we're going in the positive departure direction, or we're going positive east, more east. So what if we had coordinates? Generally, we assumed beginning coordinates of our control point 1 last semester, and I'll just throw generic northing 5,000, easting 1,000 coordinates on here. To get or compute the coordinates of control point 2, the northing of control point 2 is equal to the northing of control point 1 plus the latitude, because remember, the latitude is strictly a component in the northing direction. Northing of CP1 is 5,000. We add the latitude, and remember, that's the importance of this sign. Adding a negative number in this case means we're going south, and we get a northing component of 4630.21 for CP2. Same with the easting. Easting of 2 is equal to the easting of 1 plus the departure, or 1,000 plus 983.48 for a 1983.48. and those are the coordinates of CP2. So really, with a little bit of trigonometry application, coordinate computation is simply adding and subtracting. This is a good concept because we're not going to be running a traverse this semester anymore. You know how to do that from last semester. We're going to establish a traverse, but we're going to lay out points with respect to the coordinate system attached to the traverse. The process of laying out a point is the exact same. We're going to be given, well, it's the exact same in reverse. A stakeout point, so say if we had 4 points, the locations of a building, we would know the coordinates of those buildings. If we know the coordinates, we can work backwards, compute a component and a component, and if we have the departure and latitude components, we can then compute an angle and a distance, and that's radial stakeout. If we set an instrument on control point 2 here, and we backsite control point 1, and we want to stake out a building corner location up here, we want to know the angle to turn and the distance to shoot. So we're performing this math essentially in reverse. So if you were comfortable doing it last spring, you're going to be comfortable doing it this fall. Even more comfortable this fall, honestly, because we're going to let a data collector's field computer perform most of these calculations for us. But I still think it's important for you to refresh your memory and understand the basics of how this is done, even though we're going to take advantage of technology this semester. Vertical calculations. This is a set of differential level notes. Hopefully this looks familiar to you. We're establishing the same columns as we did last semester. Station, backsite, HI, side shot, or you could call that an intermediate foresight, and elevation. We always have to start from a known benchmark, and what makes it a benchmark is that it has a known elevation, either assumed or true with respect to some sort of recognized datum. Recall, we always add the numbers in our backside column. We always subtract the numbers in our side shot or foresight column. So the first calculation, we're starting at a known elevation of 200. We add our backside to establish the HI of our instrument. And I'm going to put values that were derived by adding in green. I'm going to put values that were derived by subtraction in red here for you. So we have our elevation, add our backside to get our HI. We then come down to our first foresight to turning point number 1, subtract the foresight to get the elevation. So 200 plus 4.78 is 204.78 minus a 5.12 equals a 199.66. And that is the elevation of turning point 1. And it's kind of that sequence, that back and forth sequence of adding then subtracting that allows you to reduce a series of differential level notes. Hopefully this is second nature to you and you remember this. So I'm just going to throw in all of the results here. And if you were to work through these notes yourself, hopefully these are the numbers that you also came up with. We repeat the process. 199.66, add the backside to get the HI, subtract the foresight to get the elevation. Add the backside to get the HI, and here's the only nuance that comes into play, is when I see side shots, I see multiple points or multiple readings from the same instrument location my instrument height is not changing. So when I subtract, I'm not accumulating that subtraction in my results with a side shot. Because I'm not moving, my instrument's not changing, my HI stays the same. So my HI of a 209.73 minus 523 gives me 204.50. I then come back to the 209.73 minus the 512 gives me this result. And I keep coming back to my HI to subtract the side shot until you can tell in your notes that you've moved, and you move when you see an actual foresight. So 209.73 minus the 642 gives us a 203.31. Add the back sight, get a new HI, subtract the closing foresight to get a closing elevation. And I know it's a closing foresight because I'm back here citing my original starting point, a benchmark A again. We always want to perform a math check on differential level notes. You want to check your closing calculated point against your starting point or starting elevation. And we have 201.01 calculated minus a 200 known for a positive 0.01 feet. When you begin and end on the same point, the sum of your back sights should equal the sum of your foresights. And if we total up our back sights, we get 18.52. If we sum up our foresights, we get 18.51. Back sights minus foresights gives us a positive 0.01. And that's the same difference when we looked at our calculated closing minus our initial elevation. This doesn't mean your level loop is good, necessarily. It just means that your math checks and you didn't perform any math errors when you were computing these numbers over here. If these numbers are outside the tolerance that you can live with, say you've eaten up all of that contractor's tolerance, they need you to be 5/100ths accurate, and you're already at 5/100ths in your confidence in your vertical elevations, you would want to redo that level loop. You would want to make sure you're more confident on your primary control points, if you had any that you were leveling through, before you went and accepted those elevations for future work. I hope this review was helpful for you, and we will perform some of these exercises in the field this week.